Assalamualaikum. My name is Tuan Nurul Afiqah binti Tuan Putera, and I'm going to present my final year project entitled of Modeling and Design Analysis of Piezoelectric Symbol Transducer PCT Array for Roadway Energy Harvesting System. My supervisor is Dr. Boon Ching. Okay, so as for the abstract, the shortest resource of non-renewable energy has led to the new inventions of such as piezoelectric energy harvester. The piezoelectric energy harvester managed to convert the axle loading from travelling vehicles into useful electrical output, where it can be used to power up street lamps or sensor. In this project, the array configurations of PCT with the conditioning circuit for roadway energy harvesting application is as the means for its energy harvesting capabilities. Okay, as for the objective, the first one is to improve the total energy yield of symbol piezoelectric with proper array configurations, and the second one is to design the power conditioning circuit for symbol piezoelectric energy harvesting system. As for the scopes are according to the objective 1 and also objective 2. As for the objective 1, the scopes are: the prototype will be only test for 8 cells of piezoelectric, and the simulation test will be carried out using COMSOL software. The test will be using PZ85H type only. The scope for objective 2, the design will be done using electronic concept only, and the circuit will be simulate using Proteus software. So, we proceed to the design and modeling words. This is the process flow of the design model. As you can see here, is the first step is to we have designed the single PCT. The second step will be array PCT design, and then the platform. The fourth one is the pavement, and the last one will be the design of power conditioning circuit. So this is the design of PCT model, the single PCT model, and this is the design of array PCT model, and this is the platform, and this is the material properties for overall PCT model with the platform. The structural steel is being implemented for the platform of and then the PZ85 is for each PCT, and the steel is for the each top and bottom MCAT of PCT. And the copper will be implemented for the electrode for each PCT. So this is the design of asphalt pavement. The dimension for the asphalt pavement, this is the top and this is the bottom, having a height of 60 mm. So this is the material properties. And the last one is the power conditioning circuit design. So as we can see here, this is the full bridge rectifier, and this is the boost converter, and this is the energy storage where we have used ultra capacitors. Okay, now I will be present the result and the discussions. Okay, the result and discussion has been divided by 4 sections. First is the energy yield evaluation of PCT array model. Second is the evaluation of total energy yield with damper. Third is the evaluations of the total energy yield in asphalt pavement, and the fourth is the evaluation of output from the power conditioning circuits. So, for the first evaluation, which is the PCT array model, so I will be explain the method first. So we have been used COMSOL simulation, and at the frequency response study has been used to analyze the outcome of the PCT models. A resistive load with the value maintained at 20 kilo ohm has been connected in parallel with the PCT model. Feed constraint has been set at the bottom of the PCT model, and the boundary load has been set on top of the PCT models. The electrical the electrical boundary, which consists of positive and negative terminal, has been set on top and at the bottom of each PCT structure, and for the total force applied onto the PCT model has been maintained at 30 kN. This represents the lorry load of a single tire. So this is the graph or the outcome from the simulation of energy yield of PCT array. So as we can see here from this data, when the frequency increase, the output voltage is also increased, and it same goes with the output power. We can see that as the frequency increase, the output power is also increased. So this result indicates that this result has found that the frequency is significantly affect the electrical energy generated from the PCT model. This result has been aligned with the recent studies by Jiang, which has indicated that the maximum power can be harvested is proportional to the input frequency. This study has been focused on the frequency, as the frequency represent the speed of the vehicles in a real practice. The speed of the vehicles can be converted into the time of compressions. The compression exit from the surface of the vehicle tire will cause the PCT model to generate an electrical charge. The force applied needs to be evenly distributed on the PCT array model in maximizing the output power. Thus, the time of compressions can significantly affect the total energy yield. Therefore, it can be suggested that a higher frequency can increase the PCT array model's output power. Okay, now we proceed to the evaluation of total energy yield with damper, the second simulation. So this is the model. On the top of the PCT, the damper has been placed on top of the PCT model. The dimension is the same as the platform of the array PCT. The method is that the resistive load is varied from 10 kilo ohm until 50 kilo ohm to analyze the output power and output voltage from the PCT array model with damper, and the frequency is maintained at 100 Hz, and the total force is also remain at 30 kilo N. So this is the outcome from the simulations. Okay, we can see that here that the increase in resistive load also increase the output voltage. As for the output power, we can see that the highest or maximum output power is 80.4 milliwatt at 20 kilo ohm resistive load. So this study indicate that a higher output power can be achieved by applying the damper on top of the PCT model compared to the previous simulation results. So this result can be explained by the fact that the hard rubber damper can provide elasticity and damping, which act as a spring and damper. The damper has eventually enhanced the effectiveness of the suspensions on the PCT model. The high resilience of hard rubber can limit the amount of pulling up and thus increase the effect of PCT array model. Moreover, the damper also can protect the PCT array model from destroy and increase the life expectancy of PCT array model in pavement. This observation might support the hypothesis that utilization of damper can improve the output power of the PCT array model. So, we proceed to the third evaluation, which is the evaluation of total energy yield in asphalt pavement. So this is the figure of displacement takes place on the PCT model, temper and the asphalt pavement. So this one is the electric potential distribution on PCT model. So I will explain the methods. The fixed constraint have been implemented at the bottom of the asphalt pavement, and the boundary load is placed on top of the whole model, which is at here. The simulation is carried out by varying resistive load from 10 kilo ohm until 50 kilo ohm to determine the optimum generate output power. So this is the outcome from the commercial simulation. So as we can see here, the increase in resistive load have increased the output voltage. As for the output power, we can see that the highest value of output power is at 109 milliwatt at 20 kilo ohm resistive load. So from this data, it can be seen that the external electrical load resistance is one of the significant roles in determining the level of the electrical power of the PCT area model in asphalt pavement. Based on the simulation analysis, we can see that highest one is 100 milliwatt at 20 kilo ohm resistive load with the frequency of 100 Hz. Okay, so assuming taking the power produced from the two axles vehicles, the design PCT array might produce 0.218 volt for vehicle loading. Assuming that the traffic volume is 2000 vehicle per hour, it can be estimated that the possible output power harvest from the PCT area model is about 436 watt per hour. So this amount of electrical energy is significant and can be stored in the battery to power up the road appliance such as street lamps. Okay, so now we proceed to the evaluation of output from power conditioning circuit. So this is the design power conditioning circuit. Okay, the input voltage is set to 65 volt at a frequency of 100 Hz. The input voltage value was taken from the simulation of PCT area model in asphalt pavement using console. The resistive load is varied from 10 ohm to 100 ohm. The duty cycle is set maintained at 75%. Okay, so we see that first one is the VDC from the full bridge rectifier first. So as we can see, the output voltage is at 34.5 volts. So to prove this value, we have compared with the calculate formula, which is VDC equals to 2 Vp over pi. So the value is around 41.38 from 41.38 volt. Okay, so I can explain that most all electronic equipment are in direct current basis. So thus, in order to utilize the AC voltage generated from the PCT area model, this rectification process need to be considered. The highest speed, the highest speed is 34.5 volt. Okay, so as we can see from the we calculate and also from the simulation, there is only slight difference between it, and where the percent error is around 16.63% error. So this I've been told. Okay, so this is the result from the output power and output voltage from the overall power conditioning circuit where we have been taken from this part. I will show this one, this multimeter for volt, and also the current we have measured in Proteus. So as we can see here, when the resistive load increase, the output voltage and also output power is increased when the resistive load increase. The highest output voltage is 75.5 volt, and the highest output power is 283.76 watt. So we have compared this output voltage with the calculate one, which with the formula of V out equals to D over 1 minus D Vs. So it was found that the calculate one is 103.5 volt. So if we compare to the simulation, which is the 75.5 volt, the percent error is about 27.05% only. According to this data, we can infer that this purpose power conditioning circuit can increase the input voltage of the PCT array model. The ratio of the output voltage to the input voltage is simplified to 2:1. This shows that the power conditioning circuit can boost 2 times the input voltage. This is the output current where we have used to calculate the output power. This is the simulation that has been done. This is the PCT model, and this is on top of it is the damper, and this is the asphalt pavement on top and at the bottom of the PCT model. So this is the displacement. We can see that when the force applied, it has been displaced. It has been displaced at this around this millimeter. As for the electric potential, this is the electric potential distribution on the PCT model in asphalt pavement with damper. So this is the power, the graph of the power. With the increase of frequency, we can see it is increasing. So the voltage also, when the frequency increase, the voltage increase. And the load dependence power, we can see that at 20 kilo ohm resistive load, the output power is around 109 milliwatt. And we can also see that as when the resistive load increase, the output voltage is also increased. As for the conclusion, overall, one of the most significant findings from this study is that the PCT array with damper implemented in asphalt pavement model has produced a maximum output power of 109 milliwatt with an optimal resistive load of 20 kilo ohm at frequency of 100 Hz under 30 kilo N force applied. It is found that the PCT array model with damper produce high electrical output compared to the PCT array without damper. The simulated design circuit rectified the AC input voltage of 65 volt 100 Hz to 34.4 VDC. The VDC output voltage is then boosted up to 75.5 volt. It is found that the purpose conditioning circuit has more than double of its input voltage. Thus, the objective of this study in improving the total energy symbol piezoelectric with proper array configurations as well in designing the proper conditioning circuit for the PCT have been achieved. A limitation of this study is that the simulation result has not been compared to the experiment data from the real practice of PCT model in asphalt pavement. The total energy yield might be differ as experimental work can provide the empirical data while the simulation works cannot. In spite of its limitation, the study certainly adds to the understanding the potential of PCT array with conditioning circuit applied in roadway as energy harvesting system. Okay, so for the recommendation for the future works, first is we can change the array the array type by using stack array design PCT. The stack array design PCT has been found that it can provide higher output power due to the grid stable position under the loading time. The second one is the synchronous rectifier MOSFET. Okay, as for the full bridge rectifier, we can change the rectifier, the normal diode, by using synchronous rectifier MOSFET. This is because voltage drop is smaller than the diode in full bridge rectifier. So as for the last recommendation is power management IC such as BQ25505. So this is for the can be replace the boost converter, because this IC can provide conversion efficiency up to 90%. So that's all from me. Thank you.